Wait. Okay. Okay. Sorry, I didn't update today's first part of the slide. So you all have the exam? Anyone not have the exam? Okay. One person still doesn't have the exam. Any questions before we get started? Okay.
All the questions that we did, how can you get with the questions before?
What?
Because when you know the handouts, we can give them all, we can take them home.
Yeah. So all of the lecture tutorials are on Canvas. So if you want to look at those questions, you can find them there. I don't give out solutions for them because I sometimes use them on the exam, like you may see. So we've covered the material in lecture. It's a little bit in the homeworks. Does that make sense? I don't want to just tell you where to find it, but the lecture tutorials are on Canvas.
So it's on campus.
Okay. Any other questions? So we did have a couple modifications. If you did question 5C, I guess I should just write this down, huh? And that's what that's. It says visible light, or it says light, I mean visible light. Slight change to 5C. And if you don't know what a nanometer is, NM, that's of the wavelength. So I want to make sure that it's in the lecture notes.
So what 5C, what is it?
So it says, does the Earth emit light? I mean visible light. Because if you came to the conclusion that it emits infrared light, that would be correct. But you might be taken aback by the fact that it's infrared light. I want to insert the word visible there. If you write it and you, does the Earth emit visible light at night? Okay, whatever you write, as long as you explain your answer, right, I'll give you credit for it. But it's just a point of clarification. Okay. Any other questions? Okay, I'll have normal office hours. If you have questions, you can put them in the Slack. You can email me questions, points of clarification. And then this will be due on Tuesday at the very beginning. Please note that I forgot to put anywhere on here that specifically asks you for your name. The easiest way to get no credit is not to tell me your name. Ideally, you should also put your student ID number. That just makes it easier for me to sort. Okay. Sorry, I have bad brain today. Any other questions, comments, concerns? Yeah.
Error
That I found so far, yeah. And of course, errors are always in my department. So I see an error, there's a misclarification or something, and you come to me afterwards, and you say, well, I thought you said X, Y, and Z, and you're wrong. And I'll be like, okay, you're right. Yeah. Okay. Oh, easiest way to become overwhelmed on the exam? Not to even look at any of the questions. All right, so everyone is still like thumbed through it at least. Okay, good. All right. So I'm not going to go over this. This is here again. Let's get the brain moving. We'll do a little bit of talking, and then we'll do a lecture tutorial, and then everything that is covered today essentially will be on the exam until if we get to like Jupiter, in which case that won't be on the exam, but you already know that because you all looked at it, right? Right? Okay, good. Okay, so why does the Earth have so little atmospheric carbon dioxide? I'm not ready for a question. It's like, ease me into it. Yeah.
It's stored in rocks.
Rocks. Yeah. I love one-word answers. Rocks is a good one-word answer. Okay. Anyone know what kind of rocks? Limestone. Very good. Okay. It's extremely soluble in liquid water. So in the presence of liquid water, CO2 dissolves into the ocean. And then it becomes sequestered, becomes rocks. And those rocks get recycled underneath the magma. They become atmospheric again, that comes out of the magma, goes back up into the atmosphere, and it starts to cycle again, right? What were the products of outgassing? I think we talked about this briefly. We're going to go over it again. Yeah. The products of, well, that's correct. That's where you get it. But what is the stuff that comes out of the volcano? Not just magma, the gas.
Sorry.
Carbon dioxide, sulfur gases stuff. Pretty good. 2 for 4. Anything else? Nitrogen. Wait, do you have the slide? Is that what you're looking at?
Yeah.
Okay, and then good notes, really good notes.
Water.
Water, good. So what happens to all of them? Let's go through that. Okay, water, carbon dioxide, nitrogen, SO2. Water, great. On Earth, stays in liquid form. Rains, precipitates out. So that's not very much in the atmosphere. Mostly it's in the oceans. CO2, well, great. And actually SO2 too, sulfur dioxide also is trapped by water. So these come out of the atmosphere. What are you left with? When you breathe, you're breathing nitrogen, like 70–80%. It's actually only about 20% of what you breathe is oxygen. That's okay. You actually don't want too much oxygen because oxygen is quite flammable. If you're in a pure oxygen environment, your phone goes off, it explodes. Okay, nitrogen is in the way to make sure things aren't too flammable. Okay. This process makes sense why we have a nitrogen-rich environment. Okay. I said that. Right. So oxygen is hard to create and keep around. It is not the main product of outgassing. It wasn't up there. It's extremely reactive, like we just said. This is what makes fires go boom. Right? Pure oxygen environments are extremely dangerous. Where does it come from? Trees, yes. So specifically life, but it's a biological process. What happens is we have this symbiotic nature. So we are breathing in oxygen and we're putting out carbon dioxide, and plants and things that do photosynthesis are taking carbon dioxide in and they're putting out oxygen as a byproduct. This is extremely unusual. Okay. Life is the only explanation for the distribution of oxygen in the atmosphere. So nitrogen makes sense, that comes out of it normally. And in fact, you would imagine that if you didn't have life, but you had an ocean, you had everything else on Earth, you could imagine a perfectly fine situation where most of the atmosphere is just nitrogen. Very little CO2 because it gets dissolved into the water. And there would be no free oxygen, right? With the nitrogen rich. It's only the presence of plants that gives us the ability to breathe. If we talk later in the semester, we can do like I have this lecture that I like, which is just the history of everything all the way back. And you'll see there that in one of the turning points of Earth, basically plant life did itself a real disservice because at first it was doing a really good job just taking in carbon dioxide. And then it got really good at doing that, so much so that it changed the atmosphere as a whole and killed off a lot of its friends in doing so. So it made the atmosphere, which it was breathing, carbon dioxide rich, into an oxygen rich environment, which is actually poisonous to plants, if you think about it, right? Same way that we breathe in carbon dioxide, we die. They breathe in too much oxygen, they die. And that's what happened. Okay. So this goes into that Earth's built thermostat. we talked about this nice having two cycles in here. It's self-correcting. The timescales here are tens of thousands of years. So it's not as simple as, you get home, been hot all day, turn on the thermostat, it's like a few minutes and it's nice and cool. This here takes tens of thousands of years. And the process is, for example, if it's too cold, you won't precipitate out of the atmosphere, that carbon dioxide, it'll start to build up. As it builds up, it traps the infrared light close to the surface, and that heats up the atmosphere as a whole, right? Similarly, on the right-hand side, if it gets too warm, that causes precipitation, right? More dissolved CO2 will end up in the rainwater, and the CO2 concentration will decrease in the atmosphere. Questions about this? Cool, right? Okay. So this is a fun little experiment. You can think about what's called the snowball Earth. Millions of years ago, Earth got colder than average, and the ocean started to freeze. True story. You can see geologic evidence of this, including glaciers at what would be Brazil. So not the Earth that we think about on a day-to-day basis. So how does this affect reflectivity? The whole globe is frozen over. Yeah.
It reflected our light, which didn't allow for ice to.
Right. So when we think about this in terms of like light versus dark colors, light is more reflective. So that visible light that makes it to the surface then just bounces and heads back out without being absorbed into the atmosphere. That brings the temperature down, right? So why aren't we still frozen today? Because of greenhouse gases and this thing that we just talked about with the CO2 cycle. Okay. So here's an example of negative feedback. We talked about that in the context of feedback before, positives and negatives. So here you have the growing polar caps, volcanic outgassing. The reflectivity goes down, more stuff freezes, and you get glaciers at the equator. But we talked about the fact that if you freeze the oceans over, I can no longer take the CO2 and dissolve it into the water. So now I have ice anyway. Right, so now I have a separation between these two reservoirs, the place that I have the CO2, the outgassing, the place that I want to store it in the ocean. And so CO2 starts to build up, builds up, builds up, builds up, and then it melts. And it usually overcorrects. So the whole world then melts. Great, not so good. So think about it this way. As you begin to melt the poles, as you begin to melt the ice, now the reflectivity, instead of being high light, it's now very dark. So it's absorbing lots of light. So it was already really hot and melting, and then it overcorrects, right? And the CO2 cycle restarts. Okay. On Venus, this process never self-corrects, right? So this was a negative feedback example. This is a positive feedback example. On Venus, the absence of liquid water, the absence of the ability to cycle that carbon dioxide makes it so the temperature just keeps running away until it's 700 degrees at the surface. Okay. That's what I said. Any questions about this? This stabilization after the ice age or the snowball Earth takes even longer. We go through these swings. And when we think about habitability, which most people are concerned with, this is probably very important as a process. So if you are interested in astrobiology, it's important to think about not just, okay, we found another planet around a different star, and it looks like it might be similar to Earth. We don't know what sort of process it might be going through, right? So if this process takes 400,000 years, and for maybe 400,000 years, you're in a snowball world, life is not going to be as able to survive as it would be, right now. Okay. We like to think about this in the context of all of these processes that we've talked about. The Earth is habitable today, us being alive due to plate tectonics. Why do I say that? What about the second part? Why is volcanism helpful for habitability? Creates the atmosphere. We need the atmosphere to breathe. And in fact, if you shut off all the volcanoes, what happens? No outgassing. And if you did get into a situation where the whole planet was frozen, you couldn't get out of it now. So if you turn off outgassing and it gets too cold, you're stuck that way, right? Whereas volcanism here helps in this carbon cycle. It helps us to regulate our climate. What's this part have to do with it then? What did I say about that? Let's go back to this picture. Okay, so here's the outgassing part, CO2 into the atmosphere. And then it precipitates down into the rainwater, back into the ocean. Ocean does what to it? Turns it into rock. So that's great, but we still got to do something with that rock. We can't just have infinite rock. And this is the subduction we talked about, taking it and putting it into the magma. So Venus doesn't have the ability to put any of its CO2 made rocks into the magma anymore. It's one of my favorite planetary science theories that cannot be proven about how Venus got super messed up. And we'll talk about that when we talk about the later half of how we form the planets as a whole. But this piece here is super important. You have to be able to take crust, you have to be able to take rocks, put them underneath the crust so that they melt. And that way all of the trapped CO2 is down in the magma again, where it's not bothering us as far as like being alive. Okay. Okay. Water. Why do we care about that? Sometimes you're really hungover. Nice to drink and be able to have brain function. Your whole body is mostly made of water, right? Why does it need to be liquid? Yeah. We're not quite, at least on Earth, I don't know that we have any species that can use water in non-liquid form. I haven't seen any evidence, for example, of something that lives in the ice that eats the ice directly. Usually they melt the ice before they eat it. And I've seen nothing about an amoeba that just grabs vapor from the air without it condensing. Okay, so it needs to be liquid. It's really important to, I mean, everything, right? Okay, what about this one here? Atmosphere. Is oxygen important? This one might be a little misnomer. Yeah.
Well, isn't it, it's not important necessarily in the formation of the atmosphere, but the atmosphere traps it.
Right, so here when we're thinking about oxygen, are there species that could exist on the Earth without oxygen? Yes, in fact, that was the predominant atmosphere at the beginning, right? Didn't we talk about the fact that it was mostly carbon dioxide to start with? And there's species that were doing just fine without plants, right? They were using the carbon dioxide. So they needed oxygen in the form of carbon dioxide, but they didn't need free oxygen. So maybe this is a little bit wrong, but they're related. We want to draw that distinction. So early Earth probably needed CO2 more than we do. Right now, if it was predominantly CO2, we'd have a hard time breathing. What does the stratosphere mean again? Yes, that's exactly correct. And what is doing the trapping? The ozone. And ozone is a form of oxygen. So it's three oxygens all hanging out together. Three oxygen best friends, right? And so they're doing this, and then light comes in and it separates one and makes it two best friends and one that doesn't get along anymore. But it's okay, because then this one finds other two friends and they hang out again. Okay, that's how the ozone is replenished in the top of the atmosphere. So oxygen is actually quite important for us because it's being absorbed in the stratosphere. If it weren't being absorbed in the stratosphere, what would happen? You remove all of the oxygen, for example. What happens to ultraviolet light? Goes down to us. We look a lot more tan, great. But then what happens? We get what? Skin cancer. Terrible, terrible skin cancers. In fact, you probably don't even get any species forming because the amount of damage to the DNA is so great that you simply eradicate life. Okay, so it turns out oxygen is pretty important, not just for us, but for fully developed multicellular complex life on Earth. Okay, stable climate. We care about that? We do, obviously, but it's for habitability. Do we care about that? What?
It's just right.
Just right, Goldilocks sort of scenario, right? Are people familiar with that story? Okay. Okay. So Goldilocks scenario is that you don't want too hot a soup, you don't want too cold a soup. So life loves to live right in the middle of that. And interestingly enough, it's sort of self-propagating. So some folks, when they study astronomy for long enough, they recognize that, like, okay, we live on the planet, but we are also the planet. Does that make sense? We're made of all of this stuff, and all this stuff is made of us. Does that make sense? We're made of things that we eat. So we eat the cow eats the grass eats the earth, but all of that is from the sun at every single stage. Maybe you don't eat the cow, that's okay. Does that make sense? Maybe you eat the grass. Okay. Okay, and this is a little animation I made. It's very complex. They all feed onto each other, right? Yeah, is that helpful or no? Everyone got upset with that. So how do we put these all together? So water, for example, being abundant in liquid is due to the presence of geology and volcanism. Let me see if I can go back. We'll play it again. I don't think I can do it quickly enough, but like stable climate leads to life, for example. But then also like life leads to having like an atmosphere that is filled with oxygen. So that's really convenient. Right? Okay. How do these all relate to these weird ones that we started with? Size, distance, and rotation rate? Right. Which one of these would you need to influence any of these? Size. What does size do? Volcanism, right? Yeah, so up here, volcanism and plate tectonics. Good. What about this one? Rotation rate, does that matter? Affects our atmosphere, right? Whether or not we have weather. Of these three, which would you say is the most important? Size, yeah, size definitely the most important. And then rotation rate, exactly right. And then the last one, or sorry, wait. Size. What about this one? Distance from the sun. Does that matter? So this one's a little ambiguous, right? Because if you have a big enough atmosphere, you can be far away and still warm. But you can't be too close. Because if you're too close, then you're too hot no matter what. There's no way to cool the planet off. Okay. So size is definitely the most important one. And then I will accept either one. Okay, because it's really hard to tell. Okay. Questions, comments, concerns? Okay. What if we moved Earth to Venus's orbit? Okay. It's fun, right? Years we get shorter. orbit the sun faster. You get more intense sunlight, surface temperature goes up by about 30 degrees. That's bad. That leads to evaporation of a lot of the oceans. And then we talked about the greenhouse effect. So now the light that comes in is getting trapped by all that water vapor on its way out. So here's infrared light trying to get out, and instead it's the social butterfly. It's bumping into all these water molecules because it wants to have a really good time giving them energy. As it gives them energy, it traps that heat in. Okay. And that causes more water vapor to be released. And that runs away and it gives you Venus. The process makes sense? Okay. So we're going to talk about learning from our neighbors as far as tinkering with Earth's habitability and thinking about like changing ozones and changing greenhouse gases. Let's take a little cognitive break to finish the lecture tutorials. Has anyone finished both of them? Oh, damn. Okay. I guess you guys are really cool. So I have the rest of them here. If you didn't get the telescopes and Earth's atmosphere one, this one may or may not be included as a question on the exam. And if you have questions about the exams, now you can ask them if you're already done. This is the one that I passed out on Tuesday. Oh, you need the other one? Okay, I can run to my office for you. Does anyone need this one? Okay. You need the other one too. Okay, how many people need the other one? Wait. Oh, shit.
No.
So there's one with greenhouse gases. Who does not have the greenhouse gases one? Okay, I hopefully have 5 copies. I will be right back. Yeah, I passed that out like last Thursday.
We're gonna see. It's so fun. Yeah.
Are we sure? Not being here. Okay, here's what we're gonna do. Gosh. Is this gonna work? Yeah. What's that? You guys get this one? Oh, yeah. That can work. Yeah. What's that? They're on canvas. Yeah, if you have them on canvas, you can pull them up there. If you don't see them on canvas for any reason, let me know. They should be visible. I can scroll. No one cares. That's okay. Well, we'll see most of the same stuff. Okay, so yeah, is it Saturday?
It would still be.
So I'm gonna find my.
Yeah.
What are you doing? Okay.
I lost it. I have tickets, if they go to the NLCS, I have tickets to next Wednesday too. So that's my. What? Yeah. Yeah. Oh, I didn't. Yeah. I got you.
Like that.
Yeah, I remember.
But I think. Yeah. Like 7%.
Yes, it's potentially staying. percent of energy given off by the sun.
So it would make 7% out. Yeah.
This is, total. If you add this up, 44%. All of it. Oh,
I think that I don't know, I feel so like very like, you know.
Is anyone actually using this? No, right? No, I don't think so. Cool, thank you. Good.
Yeah, I know that they're used to it right now, but I have these one of them. There's no way. Well,
Folks, we're gonna continue. I recognize probably not everyone is done. That's okay. Okay, let me ask you a question, potentially contentious. Everyone okay with this? Contentious questions? Climate change. Global warming. Is it real? What was that? I have, some people, you know, they have strong opinions. Okay. Are humans the cause? Okay, so two does. Let's back up those does with some evidence and let's think about this. Unfortunately, when I first made these slides in 2016, the answer was duh, and it still is duh, and it's duh even harder. So let's talk about what's going on. Okay, so we saw that the Earth goes through natural cycles of CO2, right? Right?
Yeah.
Yeah. So the question is it possible to push our system too far? And what would that look like? What would that mean? Okay. This is like the part of class in all months. Okay. Well, doom and gloom. So let's look at the temperature cycle over the past 400,000 years. So how do you construct this? Well, you can take core samples, specifically ice. Those go back really far. You go into Antarctica and you drill down like a kilometer and you can look at the temperature in little air pockets. It's really strange to think about. And it goes up and down. This is relative to an amount 0 here, which is normalized right around us. And you go back and you see, okay, it was 8 degrees colder. It got a little bit hotter, colder, a little bit hotter. And you might be thinking, well, climate change, that's just normal, right? Let's zoom in. Here we talked about CO2 levels. We've heard this probably a lot, right? Tired of CO2? Okay, here's the CO2 concentration from 1750 to today. What's the major cause of CO2 increase? Burning fossil fuels. That starts when? Industrial revolution with the burning of coal. Yeah, wonderful. That's smart they were thinking. Okay, so they were like, let's make more things faster, better for more money. And they had no idea what the impacts of that would have. And that's the world we live in today. So CO2 concentrations are 30% higher than before. Does temperature depend on CO2 levels? Yes, why? It's a really efficient greenhouse gas. It's not the most efficient greenhouse gas. What's the most efficient greenhouse gas? Water vapor is. Okay, but they play on each other. So it's a self-perpetuating problem. The hotter it gets, the more evaporation you get, the more water vapor you get into the atmosphere, and then the hotter it gets, right? So when we tend to talk about CO2 concentrations, it's a hallmark for bad things. Because the amount of CO2 concentration is something that we can control. The amount of water vapor in the atmosphere, in fact, we cannot control it. That's simply out of our ability to control it. Okay. And of course, if you plot these over one another, you see the temperature variations coincide quite well with the increase in CO2 globally. Okay, so here's CO2 fluctuation and then the variations in temperature. And so you say to yourself, it's not so bad. Temperature variations haven't gone up that much. But let's look at this piece here. Right? The atmosphere has a natural lag between what we do to it and the response that it has. And in fact, we're only starting to see this now. So here's how we think about this data set. Okay. And unfortunately, this was true 8 years ago when I wrote it, and it's even more true today. which sucks. So this is the way that you look at thermometers as a function of time. So you go back to the 1800s when we first, 1880s, when we first started taking very consistent temperature measurements around the world. When you average those up, and then you get the mean over the past, you see that all of the really, really hot ones are over here. You might be thinking to yourself, well, what happened in the 30s? That was totally okay. This is normal. But if I told you this was your bank account, you'd be pretty excited, right? Like this is college, you got your first job, you got laid off, and now you're really making money. Unfortunately, this is not your bank account. This is CO2 over time. Okay. So are humans the cause? Yes. Okay, maybe I don't need to say this in as much detail. We'll fly through this material. Here's what you can do to show that. If you look at just outgassing, right, that is a place that we do get CO2 from. We talked about that in detail. And you can talk about like the sun is itself changing and it's putting out more or less energy on a day-to-day basis. Kind of weird to think about. These are really small changes. So you see these fluctuations, they go up and down, up and down. Outgassing events will add more CO2, but then as we said before, it gets sequestered into the ocean, gets turned into rock, not a big deal. The problem is that if you keep putting out more CO2 than the ocean can take away, it builds up. And sure enough, this is what would be happening right now. You'd have this sort of variation around zero in the absence of any man-made CO2. So bummer. We are here. When you think of these, it's really hard to conceptualize. Like a temperature difference doesn't really mean that much to us intuitively. But like it was 65 when I left my house. Now it's like 80. I'm like, we can live through that, but that's not a big deal. But those types of small weather patterns are things that we experience on a day-to-day basis. That's not an average. So when you think about this as an average with time, every additional increase in temperature is a little bit more evaporation. A little bit more evaporation. And why is that a problem? Increases the temperature. So as it increases the temperature, unfortunately, again, it's a runaway process. So when you see these models and they all start shooting up like this, right? Like, oh, that sucks. Okay. These are the warnings that the IPCC has told us about. We've ignored for far too long. Okay. So the consequences of CO2 increase, we talked about that. The greenhouse effect strengthens. Okay. Usually we think about weather distributing temperatures. This is what we just talked about. It doesn't just mean warming everywhere. So in fact, we've sort of changed the way we think about this because we've seen that you can have these like crazy polar vortices. You get like snow in Texas, like for long periods of time and all the power goes out. They've never had that happen before. It's because the entire climate system is destabilized. Okay. So this is not just warming everywhere. And in fact, if you have a snowball, that's not evidence that global climate change is not occurring, right? And it mostly comes from this piece here. Why does it feel like every hurricane is more intense? In fact, they are. Water vapor in the atmosphere. Increased water vapor means more things to throw. So these clouds that are smashing into people's homes are filled with water vapor, right? And so if you put more water vapor into the air, storms are actually stronger. The rotation of the earth is not changing, right? The storms are getting more intense because water vapor in the atmosphere is becoming more abundant. Does that make sense? It's weird to think of clouds as a physical thing, but in fact, they're very heavy and they can smash through objects like you can see. This part sucks too. As you melt the polar regions, what happens? Reflectivity goes down. And that is a runaway process as well. So reflectivity goes down. More of the Earth's surface is dark. It absorbs more light and the temperatures increase. Okay. Sorry. Should we just keep going? Everyone's super sad looking. Okay, is this news to anyone? Okay, should we just talk about Jovian magnetospheres? We can move past this. I know you just got an exam. Maybe you don't like this. Okay, I don't like to think about it. It's not fun. One thing that is like a long-term thought is that, of course, there have been 6 mass extinctions on Earth and life persists. So this is mostly bad for us. It's definitely bad for a lot of species, but life as a whole will probably be fine just for like millions of years. So don't be like too dreading. Okay. If you are with your uncle or you talk to your grandparent and they usually have some like rebuttals, like a climate change doesn't exist. Here's how you're going to do it. This is how you're going to make Thanksgiving really easy, right? Or maybe not. I don't know if Thanksgiving's ever easy. You say, well, it's changed before. We talked about that, right? Just cycles of warm and cold. It's just a cycle. But the major difference, of course, here is this plot that we showed. You're absolutely right. Uncle's right that climate does in fact change, but this is an unprecedented change. And you can see it in the CO2 numbers. They're just going off to the right. They're getting really large. And now that you know about positive feedback, it's not your favorite, right? Okay. What about this one? You say, oh, CO2 is a tiny amount. I can't possibly make a difference. It only makes up, I can't even say that fraction. That's so small, right? But the answer is that here we see the importance of Venus's atmosphere, and this temperature change here compared to what we actually have it at is due entirely to the presence of greenhouse gases. And you sort of know this intuitively, right? When you get into your car is not filled with carbon dioxide. It's a tiny, tiny bit of carbon dioxide in there. Mostly it's oxygen. And yet it's really hot when you get into it at the end of a long day. Right? So all of these processes can happen with just a small amount of trace gases. This one is gradually getting warmer. This is true. But that's not enough. And we saw that little graph, right? So it is true that the sun is getting slightly warmer as it goes through different parts of its life cycle. But that normally corrects itself because we have this beautiful little dial in the CO2 cycle that self-corrects. But if you can't put that CO2, dissolve it into the ocean, because the ocean's full. When I say that, I literally mean the ocean's full. The oceans are acidifying, which is what's killing off the coral reefs. Right, so it turns out all of these things that you hear about are very well related. And it shows that it doesn't account for the temperature increase. Okay. In fact, the sun is kind of wonky. Sometimes it goes up, sometimes it goes down. So recently it's been decreasing in its temperature, or decreasing its light output. This one is the one you hear the most. This is the one I can hate. So you go on some talk show and it's like some person who says climate change isn't real and some person who says it is, and that's somehow supposed to represent the facts, right? Because it's equal and balanced, but that's not how scientific consensus works on anything. Because you can have one person on either side of the stage that doesn't represent the majority, okay? Remember when we talked about science as a whole, the very beginning of the class, I know it's a really long time ago. We think about it as the process of learning these things, testing and expanding. There's certainly disagreements in the community as to what the projections will be, but no serious climate scientist thinks that this is not human-made. Okay. Sorry. Did any of that data change your view? This is a really personal question. I'm just looking around to see if anyone's, no, everyone's still just as upset. Okay, what about this one? Is the ozone hole related to global warming? Is it yes, global warming is the cause of the ozone hole? B, the hole lets through dangerous UV light, which significantly affects the surface temperature. C, the lack of ozone will let through more light. No, the UV light isn't connected to greenhouse at all. Or no, the ozone hole is too small to let through light regardless of wavelength. I'm grabbing 2 topics and putting them together. Use our fist to vote here. Let's vote on 3, 2, 1. Okay. I see a lot of correct answers. Anyone want to say what it is? Defend their argument here. It's helpful that we just did the telescopes one, right? That's just where I seem to come in handy sometimes.
I think that if there's a hole in your ozone, that means that UV light will be absorbed that one in the atmosphere,
Right.
which will get to not only to us, but it will also feed on the surface more.
Right. So here, if you chose 2 or B, the hole, if there was a hole in the ozone layer, this would allow ultraviolet light to get down to the surface, and that would warm it up. And then subsequently, that infrared light would then heat up the atmosphere. Okay. That process makes sense? Interestingly enough, the ozone layer, the ozone hole, is a process we all came together and fixed. Okay, you might not think it's possible. Ozone and stratospheric shields us from solar UV. There's this huge hole. This is the 79, and like seen pictures of the 70s and 80s, his hair is all big. That is the primary cause for this hole, believe it or not. Crazy. So the stuff that you manufacture, these aerosols, you spray them into your hair, men and women, would then just like drifts off, and it would destroy ozone. When we talked about those 3 oxygen that want to be friends, they really wanted to be friends with this stuff from the hair product. Okay, and it would take them to the positive poles, and it would just eat up all of the ozone. It was 1998. Okay, ozone abundance is way down, and everyone's like, "Oh, that's scary." And then we did something about it. We stopped producing them with that object in it. They're called CFCs, but you don't have to remember that. Okay. And it got better. 20 years. It's the second smallest that it's been, right? In 2012. And it'll probably be fully back to normal 2065. So the nice thing is if you come together, we can do some things right. Okay. Did I already say that? Oh yeah, here's the 2006, 2007. It's shrinking. Kind of hard to see. Okay, so this is when it's getting worse. It's getting better. I promise. Okay. So we talked about small changes, something as silly as putting CFCs from the aerosolized containers into the atmosphere can have huge effects. Turns out that we have to think through these things and respond to them quickly. Okay. Now, will we turn Earth into a Venus? Hopefully not. Right? Definitely not in our lifetimes. Boiling off an ocean worth of water doesn't seem plausible. Will we make it into a Mars? Mars is too hot or too cold? Too cold. Could we make Earth into Mars? No. The answer is no, because Earth is too big. Okay, we would have to suddenly shrink Earth down, or like if you believe that science fiction film The Core, somehow get in there and turn the core off, like there's a switch. There isn't, of course. So we don't have to worry about this one. Can we turn Mars into Earth? No. Why not? Too small. Okay, so people who want to turn Mars into Earth are idiots. And we can go to this in great detail at the end of the semester, but probably not now, unless you think that'll be funny. Okay, so this is the one we're worried about. Venus, very similar size, way too hot. Okay, this one, Earth's perfectly good. Let's just fix it. Okay, it's very simple. Questions, comments, concerns? Okay. That's it. That would be Earth. Okay. This is all that you're gonna see on the exam. Everything from here on out won't be on the exam. Questions before we move on? Okay, so let's talk about Jovian planets and their atmospheres. These are the cool ones. And I'm gonna update a lot of these slides as we go, because there's just more and more beautiful images from Juno. What's this one? Jupiter. What's that? Great red spot, yeah. What's this one? Saturn. What's that? Right, you like it, you should put a. There you go. What's this one? What's that? Uranus. What's that? You know that rings. That's weird. What about this one? Neptune. Would you be surprised if I told you all of them had rings? Not at this point. Not surprised by anything in this class anymore. Okay, so yeah, they all have rings. Some of them are really faint. And so, for example, with JWST, we'll include these in the next set of slides. We just saw Neptune's rings for the first time in like 40 years. You have to be really close in order to see them because they're so faint, really small pieces of ice. What's that? Earth. And this is to scale. So that's my favorite reaction. What? So you take all of the Earth, everyone you've ever known and loved, and you stick it right into this, and it's not even big enough. This is a storm larger than the Earth. Absolutely massive in scale. And when we go, we can spend so much time just looking at the Juno images. So what Juno is, it's a spacecraft that flies like basically right over Jupiter. And it looks down with a beautiful camera. They almost didn't send it with a camera. Oh my God. When you see these pictures, it's just the most magnificent. I mean, it honestly looks like what happens when you I don't know if you've ever done this. Take a plate of milk. Okay, you put food coloring. Then you put soap. Yes. It's so cool looking. Okay, I challenge you to go home and do this. Take a little bit of soap, put a little dollop of soap in the end of a toothpick, and then touch it. And you'll see what happens. And then when we go to Jupiter, you're like, well, it's the same stuff. It's not very good if you don't know what I'm talking about yet. Okay. Here you can see something that's really interesting. We'll get into this in a lot of detail. So not only is there a big old storm here, there's like these little spinny dews, right? And there's lots of different colors in the spinny dews. So you have like red spinny dews. You got these little things here. I mean, those are massive. It's like the size of the United States. If you look over here at this picture. So this looks like a lot of weather, right? And in fact, though everything we've learned about atmospheres, that's these almost all the way down. Okay. So we talked about basically two types of planets. We've talked about these small inner rocky planets, and then these giant outer gas planets. And here, these are to scale, but they're not the right distance. Okay. So if you just compare them, I go, wow, that's big, right? I don't think you can see through on here. It was like up there. This is another great image. They're just so cool. You just stare and look at them. It looks like a fluid, but it's not a fluid. So it's these are the cloud tops here. If you notice, there's this banding, right? Different colors in different directions. And it turns out we saw this really early on, and I'll make sure to put this on for next Tuesday. How does Jupiter spin compared to Earth for you? You don't remember? That's my question. Was it slow or was it fast? Okay, 2 votes for, wait. Okay, now 3 votes for slow, 1 vote for fast. What do we know about weather and rotation? They're correlated, right? How could you get a big old storm like this if it was rotating fast? And in fact, it rotates in about 11 hours. The massive, massive planet, much bigger than the Earth, is rotating even faster than the Earth. And that's why you see all of these different banded patterns. It's much more vigorous weather. Okay, yeah.
What makes it rotate?
What makes it rotate? It's basically like leftover rotation. And the way we think about this is like you start at top going, start spinning it, and there was no friction. You just did it in space. It would just spin forever. And that's essentially what's happening there. Right? This is literally leftover spin from when it first formed. Jupiter is doing two things, and we'll talk about these in great detail. It's contracting. It's getting smaller. And just like when you pull your arms in when you're spinning, let's say you're ice skating, you pull your arms in, you spin faster. Okay. That's happening here. So as it contracts, it's speeding up, rotating faster. Isn't that cool? Okay. So we can see all this banded structure here. These are actually different different chemicals in the top of the atmosphere. You have a lot of ammonia, which is a nitrogen hydrogen compound up here, giving I think the red color. And this is our friend, the great red spot. Interestingly enough, when Galileo, remember Galileo used the telescope, first person to take the spyglass instead of looking at other ships that they wanted to destroy. He's like, what's up there? And he saw this. He saw the banded structure and he saw this great red spot. So that's the first time that we know about the great red spot. Interestingly enough, this is a storm. So it's not a geographic feature like, meteor crater is a thing that you can go and stomp on and it's really there. This is like an active storm. And normally we think about, say, a hurricane, it comes and goes. These little things come and go. So you'll see multiple images of Jupiter, you'll be like, oh, this is from a different time period, because a lot of this stuff will have moved, for example. These move past each other in images, and you'll see that when we look at the Juno data. And this thing is going to dissipate. It's going to disappear in like 100 years, according to models. So if you plan on having children, they might see it, but their children might not see it. Which is pretty weird to think about. We happen to be there at the right time to see this phenomenon. And here's another picture of it, just because it's so pretty. Like, what? Are you kidding me? This is not a fake image. Whenever I look at these, I always think, no, that's someone like painted it and the paint started spilling. It looks fake, right? All of this structure is real. Am I crazy? Okay, so maybe that's a better note to leave on than the doom and gloom of climate. We're gonna stop here. We'll do Tuesday. You're gonna pass the exams in at the beginning of class. I know that'll also make you upset, but I'm sure all of you are gonna do really, really well. If you have any questions, let me know sooner rather than later. Any final thoughts? No? Okay, great.